Greetings, fellow adventurers, and welcome back to my channel. Greetings, explorers of knowledge. Join us as we embark on a quest to understand data compression. In information theory, data compression, source coding, or bit rate reduction is the process of encoding information using fewer bits than the original representation. Any particular compression is either lossy or lossless. Lossless compression reduces bits by identifying and eliminating statistical redundancy. No information is lost in lossless compression. Lossy compression reduces bits by removing unnecessary or less important information. Typically, a device that performs data compression is referred to as an encoder, and one that performs the reversal of the process decompression as a decoder. The process of reducing the size of a data file is often referred to as data compression. In the context of data transmission, it is called source coding. Encoding is done at the source of the data before it is stored or transmitted. Source coding should not be confused with channel coding for error detection and correction or line coding, the means for mapping data onto a signal. Compression is useful because it reduces the resources required to store and transmit data. Computational resources are consumed in the compression and decompression processes. Data compression is subject to space-time complexity trade-off. For instance, a compression scheme for video may require expensive hardware for the video to be decompressed fast enough to be viewed as it is being decompressed, and the option to decompress the video in full before watching it may be inconvenient or require additional storage. The design of data compression schemes involves trade-offs among various factors, including the degree of compression, the amount of distortion introduced when using lossy data compression, and the computational resources required to compress and decompress the data. As we venture forward, let's take a closer look at lossless and its impact on our understanding. Lossless data compression algorithms usually exploit statistical redundancy to represent data without losing any information, so that the process is reversible. Lossless compression is possible because most real-world data exhibits statistical redundancy. For example, an image may have areas of color that do not change over several pixels. Instead of coding red pixel, the data may be encoded as 279 red pixels. This is a basic example of run-length encoding. There are many schemes to reduce file size by eliminating redundancy. The levels of LZ compression methods are among the most popular algorithms for lossless storage. DEFLATE is a variation on LZ optimized for decompression speed and compression ratio, but compression can be slow. In the mid-years, following work by Terry Welch, the levels of Welch LZW algorithm rapidly became the method of choice for most general-purpose compression systems. LZW is used in GIF images, programs such as PKZIP, and hardware devices such as modems. LZ methods use a table-based compression model where table entries are substituted for repeated strings of data. For most LZ methods, this table is generated dynamically from earlier data in the input. The table itself is often Huffman encoded. Grammar-based codes like this can compress highly repetitive input extremely effectively. For instance, a biological data collection of the same or closely related species, a huge version document collection, internet archival, and so on. The basic task of grammar-based codes is constructing a context-free grammar deriving a single string. Other practical grammar compression algorithms include sequitur and repair. The strongest modern lossless compressors use probabilistic models, such as prediction by partial matching. The Boros-Wheeler transform can also be viewed as an indirect form of statistical modeling. In a further refinement of the direct use of probabilistic modeling, statistical estimates can be coupled to an algorithm called arithmetic coding. Arithmetic coding is a more modern coding technique that uses the mathematical calculations of a finite state machine to produce a string of encoded bits from a series of input data symbols. It can achieve superior compression compared to other techniques such as the better-known Huffman algorithm. It uses an internal memory state to avoid the need to perform a one-to-one mapping of individual input symbols to distinct representations that use an integer number of bits, and it clears out the internal memory only after encoding the entire string of data symbols. Arithmetic coding applies especially well to adaptive data compression tasks where the statistics vary and are context-dependent, as it can be easily coupled with an adaptive model of the probability distribution of the input data. An early example of the use of arithmetic coding was in an optional but not widely used feature of the JPEG image coding standard. It has since been applied in various other designs including MPEG for AVC and HEVC for video coding. Archive software typically has the ability to adjust the dictionary size, where a larger size demands more random access memory during compression and decompression, but compresses stronger, especially on repeating patterns in files' content. As we enter this new chapter, let's navigate the complexities of Lossy and unravel its multifaceted nature. In the late years, digital images became more common, and standards for lossless image compression emerged. In the early years, Lossy compression methods began to be widely used. In these schemes, some loss of information is accepted as dropping non-essential detail can save storage space. There is a corresponding trade-off between preserving information and reducing size. Lossy data compression schemes are designed by research on how people perceive the data in question. For example, the human eye is more sensitive to subtle variations in luminance than it is to the variations in color. JPEG image compression works in part by rounding off non-essential bits of information. A number of popular compression formats exploit these perceptual differences, including psychoacoustics for sound and psychovisuals for images and video. Most forms of Lossy compression are based on transform coding, especially the discrete cosine transform DCT. It was first proposed in 1972 by Naja Ahmed, who then developed a working algorithm with T. Natrijan and Kelvin Rao in 1973, before introducing it in January 1974. DCT is the most widely used Lossy compression method, and is used in multimedia formats for images such as JPEG and HEIF, video such as MPEG, AVC and HEVC, and audio such as AAC and Vorbis. Lossy image compression is used in digital cameras to increase storage capacities. Similarly, Blu-ray and streaming video use Lossy video coding formats. Lossy compression is extensively used in video. In Lossy audio compression, methods of psychoacoustics are used to remove non-audible or less audible components of the audio signal. Compression of human speech is often performed with even more specialized techniques. Speech coding is distinguished as a separate discipline from general-purpose audio compression. Speech coding is used in internet telephony, for example. Audio compression is used for CD ripping and is decoded by the audio players. Lossy compression can cause generation loss. In this section, we'll be exploring theory. The theoretical basis for compression is provided by information theory and, more specifically, Shannon's source coding theorem. Domain-specific theories include algorithmic information theory for lossless compression and rate distortion theory for Lossy compression. These areas of study were essentially created by Claude Shannon, who published fundamental papers on the topic in the late years and early years. Other topics associated with compression include coding theory and statistical inference. Moving ahead, let's uncover the hidden gems within machine learning and discover their significance. There is a close connection between machine learning and compression. A system that predicts the posterior probabilities of a sequence given its entire history can be used for optimal data compression by using arithmetic coding on the output distribution. Conversely, an optimal compressor can be used for prediction by finding the symbol that compresses best, given the previous history. This equivalence has been used as a justification for using data compression as a benchmark for general intelligence. An alternative view can show compression algorithms implicitly map strings into implicit feature space vectors, and compression-based similarity measures compute similarity within these feature spaces. For each compressor C, we define an associated vector space such that C maps an input string X corresponding to the vector norm X. An exhaustive examination of the feature spaces underlying all compression algorithms is precluded by space. Instead, feature vectors chooses to examine three representative lossless compression methods, LZW, LS, and BPM. According to AIXI theory, a connection more directly explained in Enterprise, the best possible compression of X is the smallest possible software that generates X. For example, in that model, a zip file's compressed size includes both the zip file and the unzipping software, since you cannot unzip it without both, but there may be an even smaller combined form. Examples of AI-powered audio-video compression software include NVIDIA AIVC, ACMPG. Examples of software that can perform AI-powered image compression include OpenIV, TensorFlow, MATLAB's image processing toolbox IPT, and high-fidelity generative image compression. In unsupervised machine learning, k-means clustering can be utilized to compress data by grouping similar data points into clusters. This technique simplifies handling extensive datasets that lack predefined labels and finds widespread use in fields such as image compression. As we move forward, let's uncover the untold stories and fascinating intricacies of data differencing. Data compression can be viewed as a special case of data differencing. Data differencing consists of producing a difference given a source and a target, with patching reproducing the target given a source and a difference. Since there is no separate source and target in data compression, one can consider data compression as data differencing with empty source data, the compressed file corresponding to a difference from nothing. This is the same as considering absolute entropy corresponding to data compression as a special case of relative entropy corresponding to data differencing with no initial data. The term differential compression is used to emphasize the data differencing connection. Without further ado, let's move on to the topic of image. Entropy coding originated in the ERS with the introduction of Shannon for no coding, the basis for Huffman coding, which was developed in 1950. Transform coding dates back to the late ERS, with the introduction of fast Fourier transform FFT coding in 1968 and the Hadamard transform in 1969. An important image compression technique is the discrete cosine transform DCT, a technique developed in the early ERS. DCT is the basis for JPEG, a Lossy compression format which was introduced by the Joint Photographic Expert Group JPEG in 1992. JPEG greatly reduces the amount of data required to represent an image at the cost of a relatively small reduction in image quality and has become the most widely used image file format. Its highly efficient DCT-based compression algorithm was largely responsible for the wide proliferation of digital images and digital photos. Lempels of Welch LZW is a lossless compression algorithm developed in 1984. It is used in the GIF format, introduced in 1987. The EFLATE, a lossless compression algorithm specified in 1996, is used in the portable network graphics PNG format. Wavelet compression, the use of wavelets in image compression, began after the development of DCT coding. The JPEG 2000 standard was introduced in 2000. In contrast to the DCT algorithm used by the original JPEG format, JPEG 2000 instead uses discrete wavelet transform DWT algorithms. JPEG 2000 technology, which includes the Motion JPEG 2000 extension, was selected as the video coding standard for digital cinema in 2004. In this part of the video, we'll be delving deeper into audio and analyzing its key components. Audio data compression, not to be confused with dynamic range compression, has the potential to reduce the transmission bandwidth and storage requirements of audio data. Audio compression formats compression algorithms are implemented in software as audio codecs. In both Lossy and lossless compression, information redundancy is reduced, using methods such as coding, quantization, DCT and linear prediction to reduce the amount of information used to represent the uncompressed data. Lossy audio compression algorithms provide higher compression and are used in numerous audio applications, including Vorbis and MP. These algorithms almost all rely on psychoacoustics to eliminate or reduce fidelity of less audible sounds, thereby reducing the space required to store or transmit them. The acceptable trade-off between loss of audio quality and transmission or storage size depends upon the application. For example, one 640 MB compact disc CD holds approximately 1 hour of uncompressed high-fidelity music, less than 2 hours of music compressed losslessly, or 7 hours of music compressed in the MP format at a medium bit rate. A digital sound recorder can typically store around 200 hours of clearly intelligible speech in 640 MB. Lossless audio compression produces a representation of digital data that can be decoded to an exact digital duplicate of the original. Compression ratios are around % of the original size, which is similar to those for generic lossless data compression. Lossless codecs use curve fitting or linear prediction as a basis for estimating the signal. Parameters describing the estimation and the difference between the estimation and the actual signal are coded separately. A number of lossless audio compression formats exist. See list of lossless codecs for a listing. Some formats are associated with a distinct system, such as direct stream transfer, used in Super Audio CD, and Meridian lossless packing, used in DVD audio, Dolby Trude, Blu-ray, and HD DVD. Some audio file formats feature a combination of a lossy format and a lossless correction. This allows stripping the correction to easily obtain a lossy file. Such formats include MPEG for SLS scalable to lossless, WAPAC, and Optim-free dual stream. When audio files are to be processed, either by further compression or for editing, it is desirable to work from an unchanged original uncompressed or losslessly compressed. Processing of a lossily compressed file for some purpose usually produces a final result inferior to the creation of the same compressed file from an uncompressed original. In addition to sound editing or mixing, lossless audio compression is often used for archival storage, or as master copies. As we enter this new phase, let's uncover the impact of lossy audio compression on our broader topic. Lossy audio compression is used in a wide range of applications. In addition to standalone audio-only applications for file playback in players or computers, digitally compressed audio streams are used in most videos, digital television, streaming media on the internet, satellite and cable radio, and increasingly in terrestrial radio broadcasts. Lossy compression typically achieves far greater compression than lossless compression by discarding less critical data based on psychoacoustic optimizations. Psychoacoustics recognizes that not all data in an audio stream can be perceived by the human auditory system. Most lossy compression reduces redundancy by first identifying perceptually irrelevant sounds, that is, sounds that are very hard to hear. Typical examples include high frequencies or sounds that occur at the same time as louder sounds. Those irrelevant sounds are coded with decreased accuracy or not at all. Due to the nature of lossy algorithms, audio quality suffers a digital generation loss when a file is decompressed and recompressed. This makes lossy compression unsuitable for storing the intermediate results in professional audio engineering applications, such as sound editing and multitrack recording. However, lossy formats such as are very popular with end users as the file size is reduced to 520% of the original size, and a megabyte can store about a minute's worth of music at adequate quality. Several proprietary lossy compression algorithms have been developed that provide higher quality audio performance by using a combination of lossless and lossy algorithms with adaptive bit rates and lower compression ratios. Examples include AX, LDSC, LHDC, MQA, and SCL. In this section, we'll be deep diving into coding methods, unraveling its complexities and uncovering valuable insights. To determine what information in an audio signal is perceptually irrelevant, most Lossy compression algorithms use transforms such as the modified discrete cosine transform (DCT) to convert time domain sampled waveforms into a transform domain, typically the frequency domain. Once transformed, component frequencies can be prioritized according to how audible they are. Audibility of spectral components is assessed using the absolute threshold of hearing and the principles of simultaneous masking phenomenon, wherein a signal is masked by another signal separated by frequency and, in some cases, temporal masking where a signal is masked by another signal separated by time. Equal loudness contours may also be used to weigh the perceptual importance of components. Models of the human ear-brain combination incorporating such effects are often called psychoacoustic models. Other types of Lossy compressors, such as the linear predictive coding LPC used with speech, are source-based coders. LPC uses a model of the human vocal tract to analyze speech sounds and infer the parameters used by the model to produce them moment to moment. These changing parameters are transmitted or stored and used to drive another model in the decoder which reproduces the sound. Lossy formats are often used for the distribution of streaming audio or interactive communication such as in cell phone networks. In such applications, the data must be decompressed as the data flows, rather than after the entire data stream has been transmitted. Not all audio codecs can be used for streaming applications. Latency is introduced by the methods used to encode and decode the data. Some codecs will analyze a longer segment, called a frame, of the data to optimize efficiency, and then code it in a manner that requires a larger segment of data at one time to decode. The inherent latency of the coding algorithm can be critical. For example, when there is a two-way transmission of data, such as with a telephone conversation, significant delays may seriously degrade the perceived quality. In contrast to the speed of compression, which is proportional to the number of operations required by the algorithm, here latency refers to the number of samples that must be analyzed before a block of audio is processed. In the minimum case, latency is 0 samples, e.g., if the code editor simply reduces the number of bits used to quantize the signal. Time domain algorithms such as LPC also often have low latencies, hence their popularity in speech coding for telephony. In algorithms such as MP, however, a large number of samples have to be analyzed to implement a psychoacoustic model in the frequency domain, and latency is on the order of 23 ms. Let's zoom in on speech encoding and understand its implications. Speech encoding is an important category of audio data compression. The perceptual models used to estimate what aspects of speech a human ear can hear are generally somewhat different from those used for music. The range of frequencies needed to convey the sounds of a human voice is normally far narrower than that needed for music, and the sound is normally less complex. As a result, speech can be encoded at high quality using a relatively low bit rate. This is accomplished, in general, by some combination of two approaches, only encoding sounds that could be made by a single human voice, throwing away more of the data in the signal, keeping just enough to reconstruct an intelligible voice rather than the full frequency range of human hearing. The earliest algorithms used in speech encoding and audio data compression in general were the law algorithm and the law algorithm. In the upcoming section, we'll be dissecting history and exploring its intricate connections to our topic. Early audio research was conducted at Bell Labs. There, in 1950 Celsius, Chopin Cutler filed the patent on differential pulse code modulation (DPCM). In 1973, adaptive DPCM. A DPCM was introduced by P. Comiskey, Nickel South, Jayant and James L. Flanagan. Perceptual coding was first used for speech coding compression, with linear predictive coding LPC. Initial concepts for LPC date back to the work of Fumitomo Etika Nagoya University and Shuzo Saito Nippon Telegraph and Telephone in 1966. During the ERS, Vishnu South et al. And Manfred R. Schroeder at Bell Labs developed a form of LPC called Adaptive Predictive Coding APC, a perceptual coding algorithm that exploited the masking properties of the human ear, followed in the early years with the code-excited linear prediction CELP algorithm, which achieved a significant compression ratio for its time. Perceptual coding is used by modern audio compression formats such as MP and AAC. Discrete cosine transform DCT, developed by Najer Ahmed, T. Natarajan and Kelvin R. Rao in 1974, provided the basis for the modified discrete cosine transform MDCT used by modern audio compression formats such as MP, Dolby Digital, and AAC. MDCT was proposed by J.P. Princeton, A.W. Johnson and A.B. Bradley in 1987, following earlier work by Princeton and Bradley in 1986. The world's first commercial broadcast automation audio compression system was developed by Oscar Bonello, an engineering professor at the University of Buenos Aires. In 1983, using the psychoacoustic principle of the masking of critical bands first published in 1967, he started developing a practical application based on the recently developed IBM PC computer, and the broadcast automation system was launched in 1987 under the name Audicom. 35 years later, almost all the radio stations in the world were using this technology, manufactured by a number of companies because the inventor refuses to get invention patents for his work. He prefers declaring it a public domain, publishing it. A literature compendium for a large variety of audio coding systems was published in the EASE Journal on Selected Areas in Communications JSAC in February 1988. While there were some papers from before that time, this collection documented an entire variety of finished, working audio coders, nearly all of them using perceptual techniques and some kind of frequency analysis and back-end noiseless coding. Moving forward, we'll be taking a closer look at video. Uncompressed video requires a very high data rate. Although lossless video compression codecs perform at a compression factor of 5 to 12, a typical Lossy compression video has a compression factor between 20 and 200. The two key video compression techniques used in video coding standards are the DCT and motion compensation MC. Most video coding standards, such as the HICS and MPEG formats, typically use motion-compensated DCT video coding block motion compensation. Most video codecs are used alongside audio compression techniques to store the separate but complementary data streams as one combined package using so-called container formats. Now, we shift our focus to encoding theory, a topic that deserves our attention. Video data may be represented as a series of still image frames. Such data usually contains abundant amounts of spatial and temporal redundancy. Video compression algorithms attempt to reduce redundancy and store information more compactly. Most video compression formats and codecs exploit both spatial and temporal redundancy, e.g. through difference coding with motion compensation. Similarities can be encoded by only storing differences between, e.g. temporally adjacent frames, inter-frame coding, or spatially adjacent pixels, intra-frame coding. Inter-frame compression, a temporal delta encoding, reuses data from one or more earlier or later frames in a sequence to describe the current frame. Intra-frame coding, on the other hand, uses only data from within the current frame, effectively being still image compression. The intra-frame video coding formats used in camcorders and video editing employ simpler compression that uses only intra-frame prediction. This simplifies video editing software, as it prevents a situation in which a compressed frame refers to data that the editor has deleted. Usually, video compression additionally employs Lossy compression techniques like quantization that reduce aspects of the source data that are more or less irrelevant to the human visual perception by exploiting perceptual features of human vision. For example, small differences in color are more difficult to perceive than are changes in brightness. Compression algorithms can average a color across these similar areas in a manner similar to those used in JPEG image compression. As in all Lossy compression, there is a trade-off between video quality and bitrate, cost of processing the compression and decompression, and system requirements. Highly compressed video may present visible or distracting artifacts. Other methods other than the prevalent DCT-based transform formats, such as fractal compression, matching pursuit, and the use of a discrete wavelet transform DWT, have been the subject of some research, but are typically not used in practical products. Wavelet compression is used in still image coders and video coders without motion compensation. Interest in fractal compression seems to be waning, due to recent theoretical analysis showing a comparative lack of effectiveness of such methods. With our foundation established, it's time to explore interframe coding and its relevance to our overarching theme. In interframe coding, individual frames of a video sequence are compared from one frame to the next, and the video compression codec records the differences to the reference frame. If the frame contains areas where nothing has moved, the system can simply issue a short command that copies that part of the previous frame into the next one. If sections of the frame move in a simple manner, the compressor can emit a slightly longer command that tells the decompressor to shift, rotate, lighten, or darken the copy. This longer command still remains much shorter than data generated by intra-frame compression. Usually, the encoder will also transmit a residue signal which describes the remaining more subtle differences to the reference imagery. Using entropy coding, these residue signals have a more compact representation than the full signal. In areas of video with more motion, the compression must encode more data to keep up with the larger number of pixels that are changing. Commonly during explosions, flames, flocks of animals, and in some panning shots, the high-frequency detail leads to quality decreases or to increases in the variable bitrate. Now, let's shift our focus to hybrid block-based transform formats and embark on an intellectual exploration of its various dimensions. Thumb pre-processing stages of a typical video encoder. Today, nearly all commonly used video compression methods, e.g., those in standards approved by the ITUT or ISO, share the same basic architecture that dates back to which was standardized in 1988 by the ITUT. They mostly rely on the DCT applied to rectangular blocks of neighboring pixels, and temporal prediction using motion vectors, as well as nowadays also an in-loop filtering step. In the prediction stage, various deduplication and difference coding techniques are applied that help decorrelate data and describe new data based on already transmitted data. Then rectangular blocks of remaining pixel data are transformed to the frequency domain. In the main Lossy processing stage, frequency domain data gets quantized in order to reduce information that is irrelevant to human visual perception. In the last stage, statistical redundancy gets largely eliminated by an entropy coder which often applies some form of arithmetic coding. In an additional in-loop filtering stage, various filters can be applied to the reconstructed image signal. By computing these filters also inside the encoding loop, they can help compression because they can be applied to reference material before it gets used in the prediction process, and they can be guided using the original signal. The most popular example are deblocking filters that blur out blocking artifacts from quantization discontinuities at transform block boundaries. Our focus now turns to history, an important aspect of our discussion. In 1967, A.H. Robinson and Celsius. Cherry proposed a run-length encoding bandwidth compression scheme for the transmission of analog television signals. The DCT, which is fundamental to modern video compression, was introduced by Noja Ahmed, T. Natarajan, and Kelvin R. Rao in 1974, which debuted in 1988, commercially introduced the prevalent basic architecture of video compression technology. It was the first video coding format based on DCT compression. It was developed by a number of companies, including Hitachi, Picturetel, NTT, BT, and Toshiba. The most popular video coding standards used for codecs have been the MPEG standards. MPEG-1 was developed by the motion picture experts group MPEG in 1991, and it was designed to compress VHS quality video. It was succeeded in 1994 by MPEG-SH, which was developed by a number of companies, primarily Sony, Thomson, and Mitsubishi Electric. MPEG-2 became the standard video format for DVD and SD digital television. In 1999, it was followed by MPEG-SH. It was also developed by a number of companies, primarily Mitsubishi Electric, Hitachi and Panasonic. HomePeg for AVC was developed in 2003 by a number of organizations, primarily Panasonic, Godokaisha IP Bridge and LG Electronics. AVC commercially introduced the modern context-adaptive binary arithmetic coding CAVAC and context-adaptive variable length coding CAVLC algorithms. AVC is the main video encoding standard for Blu-ray discs and is widely used by video sharing websites and streaming internet services such as YouTube, Netflix, Vimeo, and iTunes Store, web software such as Adobe Flash Player and Microsoft Silverlight, and various HDTV broadcasts over terrestrial and satellite television. Brace yourself for a deep dive into genetics as we explore its impact and relevance in our evolving narrative. Genetics compression algorithms are the latest generation of lossless algorithms that compress data, typically sequences of nucleotides, using both conventional compression algorithms and genetic algorithms adapted to the specific data type. In 2012, a team of scientists from Johns Hopkins University published a genetic compression algorithm that does not use a reference genome for compression. HAPZ-IPPER was tailored for haploc data and achieves over 20-fold compression, 95% reduction in file size, providing 2 to 4-fold better compression, and is less computationally intensive than the leading general-purpose compression utilities. For this, Chanda, Elhaik, and Bada introduced MAF-based encoding MAFE, which reduces the heterogeneity of the dataset by sorting steps by their minor allele frequency, thus homogenizing the dataset. Other algorithms developed in 2009 and 2013, NAZIP and GeneMAZIP, have compression ratios of up to 1200-fold, allowing 6 billion base pair diploid human genomes to be stored in 2.5 megabytes relative to a reference genome, or averaged over many genomes. For a benchmark in genetics, genomics data compressors, see. Let's now turn our gaze towards outlook and currently unused potential and explore the fascinating connections it has to offer. It is estimated that the total amount of data that is stored on the world's storage devices could be further compressed with existing compression algorithms by a remaining average factor of. It is estimated that the combined technological capacity of the world to store information provides 1,300 exabytes of hardware digits in 2007, but when the corresponding content is optimally compressed, this only represents 295 exabytes of Shannon information. Your feedback helps me improve, so please take a moment to leave a comment or review.